In this video, we will be taking a look at stereochemistry, in particular focusing on conformations. Before we get into the details of alkane conformations, let's look at an even simpler molecule. This is hydrogen peroxide. Now, your body has enzymes that can rid the cells of hydrogen peroxide. But imagine that the hydrogen peroxide has to fit into the enzyme active site. Thinking about this bond in particular, this is a sigma bond between the two oxygens, and a sigma bond has the electron density along this axis. So if we were to rotate around this bond, that's great. It doesn't affect the strength of the bond at all. And so in other words, there is free rotation around here. So this hydrogen, oxygen, oxygen, hydrogen can all be in the plane of the screen, or this can rotate to be in the plane of the screen, but in the opposite direction, or it could be somewhere in between. Now, if we were to look at this along the side, so imagine that we're starting here and we're looking down this way, then these OHs are aligned right on top of each other. Here, we are looking at it from this side, then one H is up, one H is straight down. Here, we have one H up and the other one is over at the side. So even with this very simple molecule, we can see how it can take on very different shapes because of free rotation around single bonds. Hopefully, that simple example has convinced you of the importance of considering the overall shape of molecules. So now let's turn our attention to the alkanes. So starting out with the simplest alkane, methane, remember this is CH4. So if we write the Lewis structure, it looks like this. But when we're thinking about the shape of the molecule, we need to keep in mind that the carbon is sp3 hybridized, which means we have a tetrahedral arrangement. So if those two hydrogens are in the plane, then these hydrogens are in another plane that is perpendicular to the plane of the screen. So one hydrogen is coming forward in front of the screen, and one hydrogen is going back behind. Now, all of these bonds are sigma bonds, and so we do have free rotation around these bonds, but if we get rotation, we don't see any difference because it's still a hydrogen atom. So with methane, we can fully describe the shape just by talking about the tetrahedral arrangement of atoms. When we look at ethane, however, we can draw our two carbons. Let's put a hydrogen in the plane and a hydrogen in the plane. So one hydrogen forward, one hydrogen going back, and over here, one hydrogen forward, one hydrogen going back. So each of these is tetrahedral, and so that's what I tried to draw, a tetrahedral arrangement around this carbon and a tetrahedral arrangement around this carbon. But we could also do it like this. Here's our two carbons, here's a hydrogen, and here's a hydrogen. Now here we have one coming forward, one going back, and then here we have one coming forward and one going back. So in both of these cases, both of our carbons are tetrahedral, but the overall molecule has a different shape. Here, these are all in the same plane, and then these are coming forward and back. And on the example on the right, we have these in the same plane, and then these forward back and these forward back. So what we're talking about here with ethane, we are actually representing two different conformations. So conformations are different arrangements of atoms in space. And a very important feature is that conformations can be interconverted by rotation around sigma bonds. So we're looking at different conformations, so different arrangements of atoms in space, and they can be interconverted by rotation around sigma bonds. So it's the same molecule, but a different arrangement in space, and by rotating along this sigma bond, we can interconvert this conformation back to this conformation. So we would describe these as conformations of each other or conformers. These are different conformations of the same compound. Your book uses the term conformational isomers, but I would rather not use that because I want you to focus on isomers as having different connectivity, and these are different conformations. Now, how can we represent different conformations? Once again, this is the same molecule, ethane, but in different conformations because we have different arrangement in space. Technically, using the dash and wedge, this is helpful to show the details of shape. So this might be showing conformation, but there's ambiguity. Is this just showing the tetrahedral arrangement around each of the carbons, or are we actually trying to show the different conformations? So using the dash wedge is not the ideal way because of ambiguity. What we can use instead is, one option is a sawhorse formula. So if you're doing some work in your garage, you might have a couple of sawhorses, and then you lay your 2x4s out across that, for example. So this is what we're talking about with a sawhorse. So now we have to see how we can apply this to showing conformations. Imagine that you are looking down the carbon-carbon bond. And so here is our front carbon, and here is our back carbon. And our front carbon, we have a hydrogen going straight down, a hydrogen up and to the left, and a hydrogen up and to the right. And then our back carbon, so now we're looking at this one, our hydrogen is straight up. We have one hydrogen down and left, one hydrogen down and right. Now, in contrast, the one over here, using the sawhorse formula, here's our front carbon, back carbon. Sorry, once again, we're looking down this way. Our front carbon has a hydrogen down. Our back carbon has a hydrogen straight down, and then hydrogen up and to the right, up and to the left, up and to the right, up and to the left. Using the sawhorse formula isn't very convenient, and so whenever you do see a sawhorse formula, you know that it is meant to represent the specific conformation. Now, something that is more useful and much more common, and this is what I want you to use, is called a Newman projection. So we're doing the same thing. We are looking down the carbon-carbon bond. So let's say this is our front carbon. So that's this one here. And then this one is represented by a circle. This is the back carbon. Now off of the front carbon, we have one hydrogen that's going straight down. And imagine if you're looking at it down this angle, then this hydrogen is going to be over here. And this hydrogen, which is coming in front of the screen, that is going to be over here. Looking at the back carbon, this hydrogen is sticking straight up. This hydrogen is behind the screen, so over here it's going to be on our left, and then this one is in front of the screen, so over here it's going to be on the right. So this is a Newman projection representing this particular conformation. This is actually easier to draw than the sawhorse. It absolutely is showing conformation. You would not use it just in general to show connectivity. So this is very clear that you are showing conformation. If we look at the second conformation, once again, let's keep this one blue. So this is our front carbon. Off of our front carbon, we have a hydrogen down, a hydrogen up and to the right, a hydrogen up and to the left. And then our back carbon is the circle behind. Here we have this hydrogen is also straight down. and then we have one up and to the right, one up and to the left. So these bonds are aligned right on top of each other. Okay, this CH bond is aligned exactly on top of this CH bond. Whereas over here, this front CH bond exactly bisects the angle between these two back CH bonds. So here our CH bond is in the middle of the CH bonds behind. Here, our front CH bond is exactly overlapping with the back CH bond. This first one is called a staggered conformation, and the second one is eclipsed. So let's continue to focus on Newman projections. So using Newman projections, this is just my framework for my Newman projection. This is the front carbon, and then this is the back carbon. So be careful, make sure that you draw your bonds coming off of your front carbon so they go all the way to the middle, and then the bonds on the back carbon, they do not come to the middle, they stop out here. Now I'm trying to show this as an eclipsed, but then when I fill in the atoms, it gets kind of hard to see. So I'm showing the back a little bit offset. I still mean eclipsed. It's just that's the closest I can get with you still being able to read it. And over here, we have just the framework, and now we're filling it in with the hydrogens. And once again, these bonds only go to the circle, not all the way in here, which means this is connected to the back carbon. This one is connected to the front carbon. Now this is the eclipsed conformation of ethane, and this is the staggered conformation of ethane. And we need to think about the torsional angle. So anytime we have three bonds. So this is whatever atom, this is whatever atom, this is whatever atom, this is whatever atom. If we are looking at 1, 2, 3 bonds, then specifically we focus on these two bonds and we want to consider their angle with respect to each other. So looking at them down this way, if they are aligned on top of each other, which is what we have in an eclipsed conformation, then the torsional angle is 0. In the staggered conformation, now if we are thinking about this and this, and the angle between them, this is 60 degrees. So the eclipsed conformation has a torsional angle of 0 degrees. A staggered conformation has a torsional angle of 60 degrees. And there is an infinite number of conformations in between. So we could have it at 59 degrees, at 59.7 degrees. So infinite number of conformations in between. Now the torsional angle is important because it leads us to consider torsional strain. And torsional strain is important because it is the first example of steric strain. So there are different types of strain that can make a molecule less stable, and it has to do with the spacing overall. So the first one that we have here is called torsional strain. And this is decreased stability in a molecule when the bonds are not staggered. So when we have a staggered conformation and a torsional angle of 60, then we have no torsional strain. If we have an eclipsed conformation with a torsional angle of 0, now we have the maximum amount of torsional strain. Any of the infinite number of conformations in between eclipsed and staggered, they're going to have somewhere in between those levels of torsional strain. So let's take a look at how the energy differs with torsion angle. So these are molecules of ethane, they just have the hydrogens colored differently. So if we can focus on these two hydrogens, the red ones, and these are both going straight up, and that means there's a torsional angle between them of 0 degrees. This is an eclipsed conformation. Because of torsional strain, this conformation is at the highest energy. If the front atom rotates, so imagine you take this and just turn it clockwise, then you are decreasing the torsional strain, so lowering the overall energy of the molecule until you reach the minimum when we have a staggered conformation. So here, this front red CH is bisecting the back red and green CHs. This is a staggered conformation with a torsional angle of 60 degrees, so there is no torsional strain, and so this is the lowest energy possible. As we continue to turn this, we are increasing the torsional strain until we get to another maximum when we have a second eclipsed conformation. If we keep rotating, we're going to decrease the torsional strain until we get to another staggered conformation, continue rotating, and we increase the torsional strain to another maximum, decrease the torsional strain to another minimum, increase the torsional strain back up to the maximum. So we're looking at a difference of 12 kilojoules per mole, or 2.9 kilocalories per mole. And so we say that we have a barrier to rotation. So we do have rotation around a sigma bond, but there is a barrier. Now, how much of a barrier is this? At room temperature, half of the molecules in a sample can go from one staggered conformation to another staggered conformation in 10 to the -6 seconds. So that is really, really fast. So this barrier to rotation is not really a barrier. At room temperature, the molecules definitely have enough energy to be able to overcome this barrier. This is why we talk about sigma bonds having free rotation. It's not entirely free. It does have to have enough energy to get up over this hill, but this is not even a speed bump. Now, you may have seen this in general chemistry. This is the Arrhenius equation. So this is the rate constant K. So as the temperature changes, we are going to affect the rate constant. We're going to affect how quickly a reaction can proceed. Now, this graph is really a representation of what's happening with the Arrhenius equation. Here we're looking at the fraction of molecules that have a particular energy, and this is the energy increasing toward the right. And we're looking at two different temperatures. Let's say this is the activation energy involved in a reaction. So the molecules have to get over this transition state to get to the products. Or it could be looking at a low energy conformation, getting over this activation energy to then make it back down again to the next valley, for example. What we can see is that at low temperature, most of the molecules have this much energy, some have lower, some have higher, but there are very few molecules that have enough energy to overcome that activation energy. The pink curve shows at higher temperature. So at higher temperature, most molecules have high energy. Some have lower, some have higher, but in this case, we have a lot more molecules under the pink curve that can overcome the activation energy. So what this shows us is that if we had a sample of ethane at higher temperature, we could get the rotation to happen even faster than the 10 to the -6 seconds. We would have to cool the sample down really, really, really low to be able to slow down this interconversion of conformations because this barrier is not really that big. So to make a long story short, molecules of ethane will be able to rotate around that sigma bond to be able to interconvert among the different conformations.